Picture standing on a beach at night, toes buried in the cool sand, gazing up at a sky so vast it feels infinite. Now imagine trying to count every single grain of sand beneath your feet. An impossible task, right? Well, here's something even more staggering. The number of stars in the observable universe is roughly 10,000 times greater than all the grains of sand on every beach and desert on Earth. That's the scale we're dealing with when we talk about the cosmos. And yet, as mind-boggling as that sounds, it's just the tip of the cosmic iceberg. Because the universe isn't just enormous, it's growing. Every second, the space between galaxies stretches wider, carrying them apart like dots on an inflating balloon. This isn't science fiction. This is the reality of our expanding universe, a phenomenon that redefines everything we thought we knew about time, space, and our place in it. What if I told you that some of the most fundamental truths about the cosmos would seem stranger than anything Hollywood could dream up? That the fabric of reality itself is stretching, pushing distant galaxies away from us faster than the speed of light, or that the universe has a shape and it might not be what you expect. These aren't just wild theories, they're conclusions drawn from decades of cutting-edge research, observations that have shattered old assumptions and opened doors to mysteries we're still trying to solve. And today, we're diving deep into 25 of the most astounding facts about this cosmic expansion, each one more bewildering than the last. Think about this. Every time you look at the night sky, you're peering into a living, breathing entity, one that's evolving in ways we can barely comprehend. The universe isn't static. It's a dynamic, ever-changing stage where the rules of physics bend and warp in the most extraordinary fashion. From dark energy's mysterious push to the mind-bending idea that space itself can stretch faster than light, these facts don't just challenge our understanding, they invite us to rethink reality. So if you've ever stared up at the stars and felt that tug of curiosity, that hunger to grasp the unimaginable, you're in the right place. Buckle up, because we're about to embark on a journey through the cosmos that will leave you awestruck, questioning, and maybe, just maybe, seeing the universe in a whole new light. Here's something that will warp your sense of place in the cosmos. Our universe has no center. That might sound impossible after all. We're used to things having a middle point, from the core of an apple to the heart of a city. But the Big Bang wasn't some fiery explosion that happened in space. It was space stretching outward in every direction at once. Imagine blowing up a balloon covered in tiny dots. As the balloon inflates, every dot moves away from every other dot, yet no single point on the surface is the true center of that expansion. That's how the universe works, except instead of dots on rubber, think of galaxies embedded in the fabric of space-time itself. Here's another way to picture it. Picture a loaf of raisin bread baking in the oven. The dough represents space and the raisins are galaxies. As the bread rises, every raisin moves away from every other raisin, with the spaces between them stretching. From the perspective of any single raisin, it would seem like it's at the center of the expansion, with all the others retreating outward. But here's the twist: no raisin is actually special. Every spot in that dough has the same view, everything else moving away as if it's the center. That's the universe's great illusion. Whether you're on Earth, a planet in Andromeda, or a galaxy billions of light years away, the view is the same. The cosmos isn't expanding from somewhere, it's expanding everywhere at once. This idea shatters our everyday intuition. We're wired to think in terms of beginnings and centers, but the universe plays by different rules. The farther out we look, the faster galaxies race away, not because they're speeding through space, but because the space between us and them is stretching like cosmic taffy. That's why the most distant galaxies appear to flee at nearly the speed of light, even though they're not moving in the traditional sense. It's the fabric of reality itself that's growing. So next time you look up at the stars, remember, there's no center to the universe, no fixed point everything revolves around. You're not on the edge or in the middle, you're part of the expansion, riding the wave of spacetime's endless stretch. Here's a cosmic puzzle that bends the rules of physics as we know them. Some galaxies are racing away from us faster than the speed of light. At first glance, that sounds impossible. Einstein's theory of relativity tells us nothing with mass can ever reach light speed, let alone surpass it. So how is this happening? The secret lies in understanding what's really moving. Those far-off galaxies aren't zooming through space like rockets. Instead, the space between us is stretching, carrying them along like driftwood on an inflating river. Think of it like this. Picture two ants on a rubber band. If the ants stay still but someone stretches the band, the space between them grows. Now imagine that rubber band stretching faster than the ants could ever crawl. The distance between them increases at a rate that's impossible for the ants themselves to achieve. That's exactly what's happening across the universe. The galaxies aren't breaking any speed limits because they're not technically moving in the traditional sense. It's the fabric of space-time itself that's expanding, and over vast enough distances, that expansion adds up to apparent speeds that leave light in the dust. This doesn't violate relativity because relativity only applies to objects moving through space, not to space itself stretching. It's a subtle but mind-blowing distinction. Light will always win a race within a local patch of space, say, within our galaxy, because space there isn't expanding fast enough to matter. But across billions of light years, the cumulative stretching of spacetime means distant galaxies can appear to recede at speeds that defy intuition. In fact, the farther away a galaxy is, the faster it seems to retreat, which is why we'll never see light from the most distant parts of the universe. They're vanishing over a horizon created by expansion itself. Here's where it gets even stranger. Because of this, there are galaxies so far away that their light will never reach us, no matter how long we wait. They're not just too distant. The space between us is growing so fast that their light is like a swimmer fighting against a current that's accelerating faster than they can paddle. This cosmic event horizon means parts of the universe are forever hidden from view, not because they've vanished, but because the expansion of space has locked them away. So while the speed of light remains the universe's ultimate speed limit for matter and energy, spacetime itself plays by different rules, stretching without limits, carrying galaxies into the darkness faster than any signal could ever bridge the gap. And here's the real kicker. This isn't some distant future scenario. It's happening right now. Every second, galaxies at the edge of our observable universe cross that invisible boundary, disappearing from our cosmic view forever. One day, far in the future, civilizations in our galaxy might look up and see only darkness, all other galaxies having vanished beyond the reach of light itself. It's a humbling reminder that the universe isn't just expanding, it's accelerating, fueled by a mysterious force we're only beginning to understand, but that's a story for another fact. We're used to thinking of the night sky as an open book, a vast, glittering canvas where distant stars and galaxies are just waiting to be discovered. But here's the humbling truth. Even with our most powerful telescopes, we're only seeing about 3% of the observable universe. The other 97%, it's already slipped beyond our cosmic horizon, not because it's too faint or too far, but because the expansion of space has carried it away so fast that its light will can never reach us. It's like standing on a shoreline watching ships vanish over the curve of the Earth, except in this case, the ocean is spacetime itself, stretching so rapidly that those distant vessels are being pulled into permanent darkness. To understand why, picture a race between light and the expanding universe. Imagine a photon, a tiny particle of light, setting off from a galaxy billions of light years away, journeying toward us at the universe's speed limit. But here's the catch. As that photon travels, the space between us and its origin point is also stretching. If the expansion is slow enough, the photon eventually wins the race, reaching our telescopes after eons of travel. But if the space between us is growing too fast, If the galaxy is being carried away faster than light can close the gap, that photon is like a marathon runner on a treadmill that's speeding up. No matter how long it runs, it never reaches the finish line. That's what's happening to nearly all the universe beyond our tiny 3% window. The light from those regions is stranded, eternally en route, lost in the expanding void. This cosmic horizon isn't fixed, it's shrinking. As the universe accelerates, more and more galaxies cross that invisible boundary, their light fading from view like stars swallowed by dawn. In a sense, we're living in a privileged moment, a sliver of cosmic time when we can still glimpse a fraction of what's out there. Billions of years from now, civilizations born in our galaxy might peer into the sky and see nothing but emptiness, their night skies devoid of other galaxies entirely. The evidence of a vast, dynamic universe, the very clues that led us to understand expansion in the first place, will have vanished beyond reach. What's especially haunting is that these hidden regions aren't just far away, they're different. The universe evolves over time, and the light we see from distant galaxies shows them as they were billions of years ago, but those beyond the horizon. They've had even more time to change, their stars burning out, their galaxies merging or drifting into isolation. We'll never know what they look like now or what mysteries they might hold. It's a cosmic curtain drawn shut, leaving us forever guessing at what lies in the darkness. And here's the twist, this isn't just about distance. Even if we somehow built a telescope with infinite power, those regions would still be invisible. The problem isn't technology, it's physics. The expansion of space has erased them from our observable universe as definitively as if they'd never existed at all. So while we marvel at the glittering 3% we can see, we're left to wonder, what stories, what wonders, what unimaginable truths are written in the 97% we'll never know. The universe, it seems, is determined to keep some secrets forever. Take a ruler and measure the distance between two distant galaxies, maybe 100 million light-years apart. Now wait, not for minutes or hours, but for millions of years. When you check again, that distance will have grown. Not because those galaxies are rocketing through space, but because the very fabric between them is stretching, like invisible taffy being pulled apart. Scientists measure this expansion with a number so precise it feels almost poetic. 70 kilometers per second for every megaparsec of space. To grasp what that means, picture this. A megaparsec is about 3.2 million light-years, a distance so vast it dwarfs our entire local group of galaxies. Now imagine 2 points in space exactly 1 megaparsec apart. Every second, the expansion of the universe adds 70 kilometers of new space between them. That's like 2 cars parked on a highway suddenly finding themselves 70 kilometers farther apart without ever moving because the asphalt itself is stretching. And this isn't just happening in one direction or in some special corner of the cosmos. Every patch of space, from the void between superclusters to the emptiness inside your coffee cup, is swelling at this same relentless rate. Here's where it gets even wilder. The farther apart two things are, the faster space carries them away from each other. 2 galaxies separated by 2 megaparsecs. They're now receding at 140 kilometers per second, 10 megaparsecs, 700 kilometers per second. It's like dots on a balloon. Blow it up a little, and nearby dots barely move relative to each other. But inflate it more, and the gaps between distant dots widen dramatically. This is why galaxies at the edge of our observable universe appear to flee at nearly the speed of light, not because they're speeding, but because the cumulative stretch of space between us and them adds up to staggering velocities. But here's the twist. This expansion doesn't just push galaxies apart, it creates new space as it goes. Think of it as cosmic repulsion woven into the fabric of reality itself. Unlike an explosion that flings debris outward, this stretch marks the birth of fresh distance where none existed before, and it's silent, imperceptible, happening right now in the room around you. The space between atoms in your body, between Earth and the Moon, technically, it's all expanding. But don't worry, you're not about to drift apart. Gravity, electromagnetism, and other forces bind matter so tightly that they overpower this microscopic stretching locally. It's only in the vast, nearly empty deserts between galaxies where expansion wins, where the universe's relentless pull can't be resisted. Now zoom back out to those two galaxies we started with, drifting ever farther apart. Their fate is sealed not by their own motion, but by the silent, inexorable growth of the stage beneath them. And with every passing second, the universe grows a little roomier, stretching into darkness, carrying its secrets with it. If you stacked every star, planet, and speck of dust in the universe on one side of a cosmic scale, they wouldn't even tip the balance, because everything we can see and touch makes up less than 5% of existence. The rest, it's a recipe of shadows and mysteries, 27% dark matter, and a whopping 68% dark energy, the enigmatic force stretching space-time faster every second. Picture the universe as a cake with ordinary matter, the stuff of galaxies, trees, and your morning coffee, as nothing more than a few sprinkles on top. The bulk of the cosmic dessert is invisible, untouchable, and unlike anything science has ever encountered. Dark energy isn't just a player in this story, it's the director rewriting the fate of the universe. For most of cosmic history, gravity was the dominant force, pulling galaxies together in a slow cosmic dance. But around 5 billion years ago, something flipped. Dark energy's repulsive push overtook gravity's grip, and the expansion of the universe began accelerating, as if an invisible foot slammed on the cosmic gas pedal. This wasn't just unexpected, it shattered decades of assumptions. Astronomers used to think expansion would slow over time, like a ball rolling uphill. Instead, they found the ball was hurling itself off a cliff faster and faster, with no breaks in sight. Here's the wild part: dark energy doesn't dilute as space expands. Unlike matter or radiation, which thin out as the universe grows, dark energy's density stays constant, meaning its influence strengthens as the cosmos stretches. Imagine pouring a cup of water into an ever-expanding pool, only to watch the water level rise instead of fall. That's the counterintuitive power of dark energy. The more space it creates, the more dominant it becomes. Some theories suggest it's woven into the vacuum of space itself, a property of nothingness pushing nothingness apart. But how do we know it's there if we can't see or touch it? The evidence is etched in light. When scientists measured distant supernovae in the late 1990s, they expected these dying stars to be closer together as the universe's expansion slowed. Instead, they found the opposite. The supernovae were farther apart than physics predicted. It was like watching footprints in the sand stretch wider on their own, as if the beach itself was pushing them. Even more telling, the cosmic microwave background, the afterglow of the Big Bang, bears the fingerprint of dark energy's grip, warping the geometry of the universe in ways only an accelerating expansion can explain. And here's the twist: dark energy might not be a force at all. Some physicists argue it's a sign our understanding of gravity is incomplete, that Einstein's equations need revising on cosmic scales. Others propose it's a temporary phase, a cosmic illusion that will vanish as suddenly as it appeared. But one thing's certain: dark energy is reshaping the universe's destiny. Billions of years from now, it could tear apart galaxy clusters, then stars, then planets, and finally the fabric of spacetime itself in a theoretical big rip. Or it might leave the cosmos cold, dark, and empty, with every galaxy stranded beyond the horizon of light. For now, dark energy remains one of the greatest puzzles in science, a silent, invisible architect determining the fate of everything. We're left staring at the sky, knowing the universe is so much more than what meets the eye, and that the answers might lie in the nothingness between the stars. Measuring the universe's expansion should be straightforward. Pick a few landmarks, track their movement, and crunch the numbers. But here's the cosmic curveball. Depending on where you look, the universe seems to be expanding at different rates. This isn't just a rounding error, it's a full-blown crisis in cosmology, one that split physicists into camps and might rewrite the rules of reality itself. At the heart of the chaos is something called the Hubble constant, the speed at which the universe stretches for each megaparsec of space. You'd think nailing down this number would be simple, but when scientists measure it using nearby stars and galaxies, they get one answer. When they look at the ancient light from the Big Bang's afterglow, they get another. And these values aren't just slightly off, they're stubbornly, glaringly inconsistent, like two clocks ticking to entirely different rhythms. Take the local approach first. By studying pulsating stars called Cepheids in our galactic neighborhood and cataclysmic supernova in nearby galaxies, astronomers can calculate distances and recession speeds with remarkable precision. These measurements peg the Hubble constant at around 73 kilometers per second per megaparsec. But then there's the cosmic microwave background, the faint whisper of the infant universe frozen in time. When satellites like Planck analyze this relic radiation, they infer an expansion rate of 67 kilometers per second per megaparsec. That 6-kilometer gap might seem small, but over cosmic distances it balloons into a chasm. It's like predicting the speed of a car based on its tire rotation, only to find the GPS insists it's moving much slower. So who's wrong? The unsettling answer might be no one. This discrepancy, dubbed the Hubble tension, has persisted despite decades of refined measurements and cross-checks. At first, researchers blamed hidden errors, maybe dust distorting starlight or miscalibrated instruments. But as techniques improved, the gap refused to close. Now, many suspect the universe is playing tricks on us, hinting at physics we've yet to discover. One tantalizing possibility: dark energy isn't constant but evolves over time, its push growing stronger or weaker in ways we haven't accounted for. Or perhaps dark matter interacts with itself in unexpected ways, subtly altering the cosmic tug-of-war. Some theorists even float the idea of an undiscovered particle, like a dark photon, subtly reshaping spacetime's behavior. Here's where things get really speculative. A few bold voices suggest our entire framework might need an overhaul, that Einstein's relativity, the bedrock of modern cosmology, breaks down on universe-sized scales. Imagine realizing the ruler you've been using bends imperceptibly over long distances, throwing off every measurement. Others propose wilder ideas, like our galaxy sitting in a vast cosmic void, a bubble of lower density that skews local observations. But each fix comes with its own problems, and so far, no solution has satisfied everyone. What's thrilling about this crisis is its humility. Science thrives when things don't add up, when the universe throws a wrench in our neat equations. The Hubble tension isn't a failure. It's a flashing signpost pointing beyond the horizon of current knowledge. Whether it leads to tweaked constants or a full rewrite of physics, one thing's certain: the cosmos has surprises in store, and the next chapter of this story might change everything we think we know about space, time, and the fabric of reality itself. The universe didn't just expand after the Big Bang, it exploded into being, ballooning from smaller than an atom to the size of a galaxy in a fraction of a second. This mind-bending growth spurt, called cosmic inflation, left behind fingerprints, ripples in spacetime so subtle they've eluded detection for decades. But if we could spot them, they'd confirm inflation happened and reveal secrets from the universe's first trillionth of a second. The key lies in gravitational waves, not the kind from colliding black holes we detect today, but primordial ones, stretches and squeezes in the fabric of reality itself, born when the universe was a seething quantum foam. These waves would have left a unique mark on the cosmic microwave background, the afterglow of the Big Bang. Picture throwing a rock into a still pond. the ripples distort the surface in predictable patterns. Inflation's gravitational waves would do the same to space-time, imprinting a distinctive curl or swirl pattern in the polarization of the CMB, like a cosmic fingerprint pressed into the oldest light we can see. Scientists call this signature B modes, and finding them would be like uncovering the universe's birth certificate. The hunt for these patterns is agonizingly difficult. The signal is buried under noise from dust in our galaxy, distortions from intervening matter, and the sheer faintness of the imprint itself. It's like listening for a whisper in a hurricane. Projects like the BICEP and Planck telescopes have come close, with a tantalizing but controversial detection in 2014 that turned out to be cosmic dust masquerading as a signal. The disappointment was crushing, but the search continues with next-generation instruments designed to filter out false clues. What makes this so revolutionary isn't just confirming inflation, though that alone would reshape cosmology. These waves could reveal the energy scale of the early universe, telling us which version of inflation, if any, is correct. Some theories predict stronger waves, others weaker. Detecting their strength would rule out entire branches of theoretical physics. Even more profound, if inflation's gravitational waves are found, they'd offer a glimpse of quantum gravity, the elusive marriage of quantum mechanics and relativity playing out on a cosmic scale. Here's the staggering part: these waves would be the oldest things we've ever observed, older than atoms, older than light itself. They're echoes of a time before time, when the universe was a frothing, chaotic place where the laws of physics as we know them didn't yet apply. And if we can decode their message, we might finally understand what sparked existence into being, not just how the universe grew, but why it began at all. So while we haven't caught those primordial ripples yet, the quest itself is a testament to human curiosity. We're piecing together the universe's origin story, one whisper at a time, chasing shadows from the dawn of reality. And if that faint curl in the CMB ever comes into focus, it won't just be a discovery, it'll be a window into the moment everything began. Right now, the universe is stretching at a predictable pace, galaxies drifting apart, space growing roomier. But what if that acceleration doesn't just continue? What if it spirals out of control? Enter the Big Rip, a hypothetical doomsday for the cosmos where dark energy doesn't just nudge the universe apart, it tears it to shreds. Picture this: trillions of years from now, the repulsive force of dark energy grows so strong that it overcomes gravity's grip, not just on galaxies, but on every star, planet, and eventually every atom. It starts with the largest structures. Galaxy clusters, once bound by gravity, are ripped apart first. Then individual galaxies unravel, their stars flung into the void like sparks from a firework. Next, solar systems dissolve, planets torn from their suns, moons wrenched from their orbits. But the horror doesn't stop there. As the expansion accelerates exponentially, even stars and planets can't hold themselves together. The same force that once gently stretched space now overwhelms the bonds of gravity and electromagnetism. Stars explode without warning, their cores ripped open by the universe's relentless pull. Planets fracture like overinflated balloons. Finally, in the last gruesome moments, atoms themselves are torn apart. Protons and electrons shredded as the space between them grows faster than the speed of light. In the Big Rip's final microseconds, space-time itself might fracture, leaving nothing. No galaxies, no particles, just an eerie, infinite silence where a universe once thrived. Here's the chilling part: this isn't science fiction. It's a mathematically plausible outcome if dark energy's strength isn't constant but increases over time, a version called phantom dark energy. Current observations can't yet rule this out. In this scenario, the countdown clock is already ticking. Some models estimate the Big Rip could happen in as little as 22 billion years, a blink in cosmic time. For context, Earth's sun will still be shining when this apocalyptic unraveling begins. But why would dark energy behave this way? The answer lies in the equation of state, a number describing how its density changes with expansion. If this value dips below -1, dark energy's push becomes self-reinforcing, growing stronger as space stretches. It's like a car whose accelerator jams harder the faster it goes. Eventually, the engine tears itself apart. The universe, in this case, isn't just expanding, it's accelerating towards self-destruction. Yet there's a haunting beauty to this idea. Unlike the heat-death scenario where the universe fades into cold emptiness, the Big Rip is violent, decisive, a cosmic crescendo. It's a reminder that dark energy, the same force weaving the universe's grand tapestry today, could one day become its executioner. And while we'll never witness it, the mere possibility reshapes how we see our place in the cosmos, not just as inhabitants of space, but as temporary passengers on a ride whose brakes might not exist. Hold a sheet of paper perfectly flat, and it stretches endlessly in 2 directions without bending or warping. Now imagine that in 3 dimensions, a universe so meticulously balanced between expansion and gravity that its geometry is flawlessly Euclidean, like a vast, uncurved plane stretching into infinity. This isn't just theoretical. Our universe's flatness is one of the most precisely measured facts in cosmology, confirmed by satellites like WMAP and Planck 2 within a hair's breadth of perfection. The data reveals a cosmic density so finely tuned that if it deviated by just 1 part in 10 to the 62nd power, that's a 1 followed by 62 zeros, space would either have collapsed back on itself or ripped apart too fast for galaxies to form. To grasp why this is astonishing, picture a pencil balanced on its tip. The slightest nudge sends it toppling, yet our universe has remained in this precarious equilibrium for 13.8 billion years. How? The leading answer lies in cosmic inflation, that explosive expansion in the universe's first moments. Think of inflation as a cosmic iron, smoothing out any curvature by stretching space so drastically that what remained became indistinguishable from flat. It's like blowing up a balloon to the size of Earth. Any tiny wrinkles on its surface would vanish, leaving it seemingly flat to an ant standing on it. But flatness isn't just about geometry, it's a clue to the universe's fate. A perfectly flat cosmos teeters on the knife edge between closed, where space curves back on itself like a sphere, and open, where it bends outward like a saddle. In a closed universe, gravity eventually wins, pulling everything back into a big crunch. An open universe flies apart forever, cold and empty. Flatness means we're precisely in between. Expansion slows but never stops, with galaxies drifting apart endlessly yet never reversing. Here's the twist: flatness also implies the universe's total energy might be zero. All the positive energy in matter and radiation could be perfectly offset by the negative energy of gravity, meaning the cosmos could have emerged from nothing without violating conservation laws. It's as if the universe is the ultimate free lunch, its mind-boggling complexity balanced on a ledger that sums to zero. The precision needed for this flatness defies imagination. If the universe's density at 1 second old had been even slightly higher, space would have collapsed by now, slightly lower, and matter would have scattered too thin for stars to ignite. That we exist at all hinges on this razor's edge fine-tuning, a puzzle that either points to an unfathomably unlikely accident or to deeper laws we've yet to uncover. Either way, the flatness of the universe isn't just a curiosity. It's a cornerstone of reality, written in the echoes of the Big Bang and the faint glow of the cosmic microwave background. And it's a reminder that the cosmos runs on a tightrope, balanced by forces we're only beginning to understand. The universe's largest structures, galactic superclusters stretching hundreds of millions of light years, owe their existence to the tiniest flickers of reality, quantum fluctuations smaller than a proton. Here's how the microscopic birthed the macroscopic. In the first sliver of a second after the Big Bang, when inflation blew the cosmos up like a balloon, space wasn't perfectly smooth. At the quantum level, particles and energy popped in and out of existence, creating microscopic ripples in the fabric of space-time. These weren't flaws, they were the seeds of everything. Picture a calm pond on a windless day. At first glance, the surface seems flawless, but look closely and you'll see tiny ripples from water molecules jostling randomly. Now imagine that pond expanding to the size of an ocean in an instant. Those infinitesimal ripples would stretch into enormous waves. That's precisely what happened during inflation. Quantum fluctuations, magnified by the universe's explosive growth, became the density variations that shaped the cosmos. Regions with slightly more particles became gravitational wells, pulling in matter over billions of years, while sparser regions stretched into cosmic voids. The result, a vast cosmic web of galaxies clustered along filaments, tracing the blueprint of those primordial quantum tremors. Here's the astonishing part: we can see these fluctuations fossilized in the cosmic microwave background. The faint temperature variations, hot spots and cold spots differing by mere millionths of a degree, are the stretched-out signatures of those quantum jitters. It's like finding the thumbprints of the universe's infancy pressed into the oldest light we can observe. Without those microscopic imperfections, gravity would have had nothing to work with, and the universe would have remained a featureless sea of particles. No stars, no galaxies, no us. But how does something smaller than an atom dictate the fate of galaxy clusters? The answer lies in inflation's insane stretching power. A quantum fluctuation spanning 10 to the minus 30 centimeters, a scale so small it makes a proton look planetary, got inflated to scales of millions of light years. That's like taking a single grain of sand and blowing it up to the size of the observable universe. And because these fluctuations were random, they created a universe that's lumpy in the most fascinating way. Matter clumped where the fluctuations were densest, forming gravitational anchors that eventually grew into the celestial structures we see today. This bizarre connection between quantum mechanics and cosmology isn't just theoretical. Supercomputer simulations that model these initial conditions evolve into virtual universes eerily resembling our own, complete with galaxies clustered in filaments and voids. It's as if the universe took its first breath during inflation, exhaling those quantum whispers into the scaffolding of reality. So next time you gaze at the night sky, remember, the grand tapestry of galaxies isn't just the work of gravity and time. It's the echo of a quantum whisper amplified across eternity, written in the stars. Imagine a photon of light born in the fires of the universe's first stars over 13 billion years ago. A tiny spark hurled into the void when galaxies were just assembling from the primordial dark. Its journey begins in a cosmos barely recognizable, where space itself was denser, hotter, and smaller in every direction. For billions of years, this photon streaks through an ever-expanding universe, not in a straight line as we'd expect, but along a stretching fabric of space-time that warps its path like a marathon runner racing on a treadmill that's constantly lengthening. At first, this light was energetic, vibrating at the ultraviolet wavelengths of young, blazing stars. But as space expanded, the photon's waves stretched too, redshifting down the spectrum like a cosmic slide into lower energy. By the time it reaches the James Webb Space Telescope's golden mirrors, that once ultraviolet light has been stretched 1,000-fold into the infrared, a whisper of warmth carrying secrets from the dawn of time. What's astonishing isn't just the distance traveled, but how the universe has rewritten the photon's very identity along the way. Here's where the story gets even stranger. That photon didn't just passively traverse space, it surfed a dynamic, evolving cosmos. Every atom, every galaxy it passed acted as a subtle lens, bending its path with gravity. Vast clouds of intergalactic gas absorbed and re-emitted it, while dark matter's invisible scaffolding steered it like a cosmic obstacle course. The photon's 13 billion-year odyssey wasn't a straight shot, it was a pinball journey through an ever-changing labyrinth, with expansion itself dictating the rules. But why infrared? The answer lies in the universe's relentless stretch. Just as the pitch of a siren drops as an ambulance speeds away, light's wavelength elongates as space expands beneath it. This cosmic redshift transforms the photon's energy so dramatically that only instruments like JWST, tuned to the infrared, can catch its faint signal. It's as if the universe encoded its history in a language only the most advanced telescopes can decrypt, a celestial Morse code stretched across time. And here's the haunting truth. By the time this light reaches us, the stars that birthed it are long gone, their galaxies transformed beyond recognition. We're not just observing the distant past, we're catching echoes from a universe that no longer exists. The photon's journey is a one-way message from a vanished era, a relic of cosmic dawn now illuminating our present with the glow of what once was. Yet the miracle isn't just that we can detect this ancient light, it's what it tells us. The redshift of these photons reveals the universe's expansion history like tree rings record a forest's growth. Each wavelength is a timestamp, a clue to how fast space was stretching when the photon passed through it. Together, they form a breadcrumb trail back to the infancy of everything. So when JWST captures that faint infrared glimmer, it's not just collecting data, it's assembling a photo album of the universe's childhood, one stretched photon at a time. Think about this: the next time you see a starry sky, some of those pinpricks of light are still traveling, their stories unfolding across the ages. And long after we're gone, new photons will continue their endless journeys, stretched, shifted, and transformed by the universe's unyielding expansion, carrying our era's light into futures we can barely imagine. Gaze up at the night sky, and you might assume our view is unique, that Earth occupies some special vantage point. But one of cosmology's most profound revelations is that the universe, on the grandest scales, looks remarkably similar no matter where you are. This cornerstone idea, called the cosmological principle, states two things. The cosmos's homogeneous matter is evenly distributed when viewed at large enough scales, and isotropic, it looks the same in every direction. To test this, astronomers have mapped millions of galaxies across billions of light years, constructing 3D atlases of the cosmic web. The result, a breathtaking confirmation that the universe truly plays no favorites. Whether you're in the Virgo supercluster or a galaxy 10 billion light-years away, the overall scenery, vast filaments of galaxies threading enormous voids, is eerily consistent. But how do we know this uniformity isn't just a local fluke? Enter galaxy redshift surveys like Sloan Digital Sky Survey and DAISY, which act as cosmic censuses, cataloging galaxies across unprecedented volumes of space. These projects reveal patterns so vast they defy human intuition. A cube of space measuring 1 billion light-years per side, for instance, contains roughly the same number of galaxy clusters and voids as any other billion light-year cube, no matter where you place it. It's like slicing a loaf of raisin bread and finding each slice has the same density of raisins, even if individual clusters vary. This uniformity isn't just aesthetic, it's a smoking gun for the Big Bang, confirming the universe expanded from an initially smooth, ultra-dense state. Yet there's a crack in this elegant picture, the so-called axis of evil. When scientists analyzed the cosmic microwave background, the afterglow of the Big Bang, they expected its temperature fluctuations to be randomly distributed like static on a television screen. Instead, they found a peculiar alignment. Some fluctuations seemed to line up with the plane of our solar system, as if the universe had a subtle preferred direction. This anomaly, whimsically nicknamed after a geopolitical phrase, challenges the isotropic assumption head-on. It's like discovering all the sprinkles on a cupcake mysteriously tilt toward your left hand as you hold it, a violation of expected symmetry that defies easy explanation. Could this hint at undiscovered physics? Some theorists propose it's evidence of pre-Big Bang structures imprinting their influence on our cosmos, or even signs we're embedded in a larger multiverse with asymmetrical properties. Others argue it's a statistical fluke or an artifact of measurement biases, but the persistence of this signal across multiple datasets keeps the debate alive. The cosmological principle remains foundational, but the axis of evil whispers that the universe might still harbor secrets about its own symmetry or lack thereof. What's striking is how delicate this balance appears. The universe is uniform enough to validate the Big Bang model, yet just uneven enough to keep us questioning. Galaxy surveys show homogeneity at scales above about 300 million light-years, but zoom in further and chaos reigns. Galaxies clump into clusters which weave into superclusters, all dancing on the edge of cosmic randomness. This fine-tuned disorder is precisely what allowed stars and planets to form too smooth, and gravity would never have sculpted the structures we call home. Too lumpy, and the cosmos would have collapsed into black holes long ago. So while the cosmological principle stands as one of science's great triumphs, the axis of evil reminds us that every rule might have its exceptions. The universe wears its uniformity like a mask, mostly flawless, but with wrinkles that could rewrite everything we think we know. And somewhere between the vast sameness of the cosmic web and the tantalizing tilt of the CMB lies the next chapter in our quest to understand the grandest scales of existence. The early universe didn't just expand, it stretched time itself, warping our perception of its infancy like a cosmic slow-motion reel. Picture this: the first 380,000 years after the Big Bang, known as the recombination era, when the universe cooled enough for atoms to form and light to travel freely, unfolds in our observations not as a fleeting instant but as an agonizingly drawn-out epoch. Here's why. As space expanded exponentially during inflation and beyond, photons emitted during those early moments got caught in the stretching fabric of space-time. Their waves elongated not just in distance but in time. It's like pressing slow motion on a video of fireworks. The initial explosion happens in a split second, but the camera stretches each frame, making the burst appear to hover in the air far longer than reality. To grasp how extreme this time dilation was, consider the cosmic microwave background, the oldest light we can see. That afterglow didn't wink into existence all at once. It emerged over hundreds of thousands of years as electrons and protons paired up to form hydrogen atoms. But because the universe was expanding so rapidly, light from the end of that process had to traverse a cosmos vastly larger than when it began. From our perspective, those final photons arrive at our telescopes almost in unison with the earliest ones, compressing eons of cosmic history into what appears as a single glowing snapshot. The result, a seemingly endless twilight of creation where time itself becomes elastic, stretched thin by the universe's explosive growth. This time warp isn't just a curiosity, it's the reason we can study the early universe at all. Without that extreme dilation, the CMB would have flashed by in an instant, leaving no detectable trace. Instead, inflation's relentless pull gave us a fossilized echo, a billion-year-long dawn captured in microwaves. Think of it as nature's pause button, freezing the universe's first breath long enough for us to decode its secrets. And here's the mind-bending twist: this same stretching affects how we perceive all ancient light. The farther back we look, the more time dilates, like a cosmic funhouse mirror where distant events appear to unfold in syrup. A supernova exploding 10 billion years ago doesn't just look dimmer, it seems to burn slower, its brilliant flash stretched into a languid glow by the expanding space its light traverses. Even the universe's earliest stars, those blazing pioneers born in the cosmic dark ages, flicker in our telescopes as if underwater, their lives protracted by the weight of expanding time. This eerie slowdown isn't just a trick of perspective. It's a fundamental feature of relativity where gravity and motion bend time itself. In the early universe's ultra-dense, ultra-fast environment, clocks didn't just tick differently, they crawled. A single second near the Big Bang, when the cosmos was hotter than a trillion suns, would pass for us like an eternity, its moments fanned out across billions of years. It's as if the universe recorded its infancy on a tape player set to the lowest speed, then handed us the playback. So when astronomers study the CMB's subtle fluctuations, they're not just mapping the universe's baby pictures. They're reconstructing a timeline warped by expansion, untangling a story where time itself is a character, bending and twisting to the will of spacetime. And buried in that stretched-out light are clues to everything: the birth of atoms, the seeds of galaxies, even the shadowy presence of dark matter. The early universe didn't just leave us a message, it gave us a time capsule, sealed by expansion and written in the slow, patient language of light. The universe has a fever chart, a cosmic thermometer tracking its temperature across 13.8 billion years, and the readings tell a story of remarkable cooling. Back when the cosmos was a seething plasma just 380,000 years old, it burned at an unimaginable 3,000 Kelvin hotter than the surface of most stars. Today, that same universe hums at a mere 2.7 Kelvin, barely above absolute zero. That drastic drop isn't just a quirk of time. It's a direct consequence of space stretching like an inflating balloon, spreading the same energy over an ever larger volume. Think of it like steam escaping from a kettle. When the steam is confined, it's scalding hot, but let it expand into a room and its heat dissipates, the energy now thinly distributed. The universe works the same way. The cosmic microwave background, the afterglow of the Big Bang, started as blindingly intense light. But as space ballooned, those photons were stretched into longer, weaker microwaves, their energy diluted by the growing vastness around them. It's the ultimate cosmic refrigeration, with expansion acting like the universe's cooling system. Here's where the analogy gets even more tangible. Your fridge relies on this same principle. Gas expands inside its coils, shedding heat as it does. The universe, in a way, is the world's largest refrigerator, with space-time itself as the expanding coolant. But there's a key difference. Unlike a fridge, which cycles gas back to restart the process, the cosmos has no reset button. Its cooling is irreversible, a one-way slide toward colder, quieter depths as expansion carries energy ever farther apart. What's astonishing is how perfectly this cooling aligns with predictions. When scientists first detected the CMB's faint glow in 1965, its temperature matched theoretical expectations almost exactly, a smoking gun for the Big Bang. That 2.7 Kelvin isn't arbitrary. It's the precise value you'd expect if the universe had stretched from a primordial fireball to its current size. Even more remarkably, as telescopes like Planck mapped minuscule temperature variations across the sky, they found fluctuations of just a few millionths of a degree, whispers of density variations imprinted during inflation, preserved in the chill. But here's the twist: the universe isn't just cooling, it's doing so unevenly. In the distant future, as dark energy accelerates expansion, the CMB will redshift into oblivion, its photons stretched so far they'll become undetectable. Galaxies beyond our local group will vanish over the horizon, their light stretched beyond recognition. The universe won't just be cold, it'll be starkly, eerily dark. And yet, even as the cosmos fades toward absolute zero, that residual glow, now a whisper of microwaves, remains a time capsule, carrying the heat signature of creation itself. So next time you open your fridge, remember, you're witnessing a miniature version of the universe's grand cooling cycle. Only instead of keeping milk fresh, the cosmos is slowly, inexorably dissipating its birthright of heat into the infinite void. And that 2.7 Kelvin background, it's not just leftover warmth, it's the final ember of the Big Bang, glowing faintly against the encroaching cold. Hidden in the sprawling maps of galaxies are ghostly echoes of the universe's earliest sound waves, an imprint so precise it acts as a cosmic ruler, measuring the expansion of space itself. These frozen ripples, called baryon acoustic oscillations, began as pressure waves racing through the seething plasma of the infant cosmos, just 380,000 years after the Big Bang. Picture the universe back then as a superheated soup of particles and light, so dense that photons couldn't travel far without colliding with electrons. In this primordial chaos, gravity pulled matter inward while radiation pressure pushed it outward, creating oscillations, regions of overdensity and underdensity that rippled outward like sound waves in water. But when the universe cooled enough for atoms to form, photons finally broke free, and those waves froze in place, leaving behind a telltale pattern: spherical shells of matter with a consistent radius of about 500 million light-years. Fast forward billions of years, and those shells evolved into today's galaxy clusters, their distribution still bearing the faint signature of those ancient oscillations. It's as if the universe stamped itself with a fingerprint, one that grew as space expanded, but whose proportions remained eerily consistent. Here's the brilliance of BAOs: they give astronomers a built-in measuring stick. By comparing the apparent size of these shells in galaxy surveys to their known original scale, scientists can calculate how much the universe has stretched over time. Imagine finding a fossilized footprint and realizing it's exactly 1 meter long. No matter how far you stretch or shrink the surrounding landscape, that footprint's true size stays the same, letting you gauge the distortion. BAOs work the same way, serving as milestones in the cosmic expansion story. Projects like the Sloan Digital Sky Survey and DAISY have mapped millions of galaxies to trace these oscillations, revealing how dark energy's grip has tightened over cosmic history. The data shows something astonishing. The shells appear slightly larger in the distant, younger universe than they do nearby. Why? Because dark energy's repulsive force only recently overcame gravity's pull, accelerating expansion and compressing the apparent scale of later BAOs. It's like watching a rubber band stretch slowly at first, then suddenly snap taut. The change in tension leaves its mark on the pattern. What makes BAOs so powerful is their immunity to cosmic dust or other observational biases that plague alternative methods. While supernova measurements depend on the brightness of dying stars and the cosmic microwave background captures a single moment in time, BAOs are woven into the very fabric of large-scale structure, offering multiple snapshots of expansion across eons. They're the universe's own calibration tool, a rhythm section in the symphony of cosmology that keeps every other instrument in tune. And here's the kicker: these oscillations don't just measure expansion, they reveal the universe's shape. By analyzing their spacing in 3 dimensions, scientists confirmed space is flat to within a razor-thin margin, matching predictions from inflation theory. It's as if the cosmos left breadcrumbs in the form of sound waves, guiding us not just through its growth but its very geometry. So the next time you see a map of galaxy clusters, remember, those seemingly random dots aren't just scattered lights. They're the aftermath of a primordial symphony, a rhythm frozen in time, echoing the universe's first notes and still singing the story of its expansion today. We think of the universe's matter as neatly packaged into galaxies, stars, and planets, but here's the cosmic twist: half of all normal matter is missing. Not hidden, not transformed, just unaccounted for. This is the missing baryon problem, one of astronomy's most persistent puzzles. Baryons, the particles that make up atoms, like protons and neutrons, should be everywhere, yet when scientists tallied up all the visible matter in galaxies and clusters, they came up short by about 50%. The math said the universe owed us an unfathomable amount of stuff, and for decades no one knew where it went. The answer, it turns out, was hiding in plain sight, or rather in the faint, diffuse glow between galaxies. Astronomers now suspect these missing baryons are strewn across the cosmos in a vast, spiderweb-like network of warm, hot intergalactic medium, or WIM. Picture steam rising from a cup of coffee, thin, wispy, and nearly invisible unless you know how to look. That's WIM. Gas so hot between 100,000 and 10 million Kelvin, it emits almost no visible light, yet so sparse that a cubic meter might contain just a single atom. These filaments weave through the cosmic web, threading the voids between galaxies, too faint to spot with traditional telescopes but massive enough to tip the universal scales. So how did we find them? The secret lies in the shadows. When light from distant quasars passes through WIM, certain wavelengths get absorbed, leaving telltale gaps in the spectrum like barcodes of missing energy. It's like holding a stained glass window up to the sun and noticing which colors don't shine through the absences reveal the glass's composition. Similarly, X-ray telescopes have caught whispers of WIM ultra-hot oxygen atoms glowing faintly in intergalactic space, while simulations show this gas should form a labyrinth of tendrils stretching billions of light years. Here's the kicker: expansion made this gas even harder to find. As the universe stretched, WIM already dilute particles spread thinner, their signals redshifting into obscurity. It's the ultimate cosmic hide and seek. The act of searching for the matter literally pushed it farther into the shadows. But why does it matter? Because these baryons aren't just filler, they're the universe's scaffolding, the raw material from which galaxies first formed. Without them, our models of cosmic evolution would crumble, and the hunt isn't over. New tools like the upcoming Athena X-ray Observatory aim to map WIM in unprecedented detail, turning these ghostly filaments from theoretical guesswork into a visible backbone of the cosmos. What we're learning is humbling. The universe doesn't put all its matter on display. Some of it lingers in the between spaces, a cosmic afterthought until you realize it's the canvas the stars are painted on. Far beyond the reach of any telescope, hidden in the direction of the constellation Centaurus, lies one of the universe's most enigmatic structures, not a glittering galaxy or a blazing star, but an unsettling absence. Scientists call it the Great Repeller, a vast cosmic void so profoundly empty that it exerts a gravitational push on our entire local group of galaxies. Picture a cosmic tug-of-war. On one side, the Shapley Attractor, a supercluster of galaxies 800 million light-years away, pulling us toward it with immense gravity. On the other, this eerie desert of nothingness, repelling us with the sheer force of its emptiness. Here's how it works. In a universe where matter clusters unevenly, voids aren't just passive gaps, they're active players in the cosmic ballet. The Great Repeller isn't merely empty. It's a region where expansion has carried away so much matter that the gravitational balance tips. Think of a crowded dance floor where everyone suddenly steps back from one spot, leaving a lone dancer unanchored. The surrounding dancers, in this case, galaxy clusters, pull toward denser areas, while the empty space effectively pushes by offering no counterbalance. It's not that the void exerts negative gravity, it's that the absence of attraction from missing matter creates a net force outward, like a hole in a rubber sheet causing the edges to sag away. But what makes the Great Repeller especially fascinating is how expansion amplifies its influence. As the universe stretches, the void grows even emptier, its edges stretching away from each other faster than the surrounding cosmic web. This runaway expansion deepens the gravitational imbalance, turning the void into a sort of cosmic riptide. Measurements show our local group, along with thousands of other galaxies, is being swept along at over 2 million kilometers per hour in a direction that aligns with both the Shapley Attractor's pull and the Great Repeller's push. Without these competing forces, we'd be drifting aimlessly in the expanding cosmos. Instead, we're caught in a river of galaxies, riding currents sculpted by the universe's largest structures. The discovery of the Great Repeller overturned assumptions about cosmic flow. Initially, astronomers thought the Shapley Attractor alone explained our motion. But when they mapped the velocities of galaxies with unprecedented precision, the math didn't add up. Something was missing, or rather, not missing. The void's repulsive effect was the hidden variable, a shadowy counterpart to Shapley's brilliance. It's a reminder that in cosmology, absence can be as influential as presence, and that the universe's grandest motions are written not just in the glow of stars, but in the darkness between them. What's haunting is that we still can't see the Great Repeller directly. Unlike clusters which blaze with starlight, voids are defined by what isn't there. Astronomers infer its existence by measuring how galaxies deviate from the smooth Hubble flow, the uniform expansion of space. These deviations reveal the void's silhouette, like deadening the shape of a cave by feeling the wind that rushes through its entrance. And just as expansion stretches space, it also stretches our understanding of gravity's reach. The Great Repeller's influence spans hundreds of millions of light years, proving that even nothingness, when writ large enough, can move the heavens. So the next time you hear about the universe's expansion, remember, it's not just a uniform stretch. It's a dynamic, uneven process that turns voids into forces and emptiness into motion. And somewhere out there, in the direction of Centaurus, a cosmic hollow we've never seen is helping steer the course of our galaxy. A silent reminder that sometimes the universe's most powerful actors are the ones we can't even glimpse. Picture a civilization born billions of years from now, in a galaxy drifting alone in an ocean of darkness. Their astronomers peer into the void with telescopes far more advanced than ours, searching for signs of other worlds, but their sky tells a lonely story. Where we see a tapestry of galaxies stretching to the horizon, they see only emptiness, not because the universe has ended, but because cosmic expansion has carried every other island of stars beyond the edge of visibility, their light stretched into oblivion by the relentless growth of space itself. This isn't just science fiction, it's the inevitable fate of any civilization arising too late in the universe's life. As dark energy accelerates expansion, the cosmic horizon shrinks like a tightening noose. Today, we can still observe galaxies billions of light years away, their light a snapshot of the universe's youth. But with every passing eon, more galaxies cross the threshold where space between us expands faster than light can bridge the gap. For future astronomers, this means the observable universe won't just dwindle, it will collapse inward, leaving their home galaxy as the sole visible anchor in an infinite black sea. Consider the existential shock this would bring. Imagine growing up in a culture where the night sky holds only a single smear of stars, your own Milky Way, with no hint that trillions of other galaxies once glittered beyond. No Andromeda, no Whirlpool galaxy, no quasars blazing at the edge of time. All evidence of the Big Bang would have vanished, the cosmic microwave background redshifted to undetectable wavelengths. Without these clues, how would they even conceive of an expanding universe? Their cosmos would appear static, finite, and profoundly lonely, their science severed from the truths we take for granted. The cruel irony is that these civilizations might possess unimaginable technological prowess capable of harnessing black holes or bending space-time, yet lack the most basic tools to reconstruct cosmic history. By the time they arise, the light from galaxies like ours will have faded beyond recovery, erased by expansion as thoroughly as if they'd never existed. Any radio signals or probes we send today will have dissipated into the void, their wavelengths stretched to meaningless noise. Future astronomers could scan the skies for millennia and find nothing but deafening silence, unaware that countless civilizations once thrived in the cosmic dawn. Here's the most haunting twist: this isolation isn't just coming, it's already begun. Right now, galaxies at the universe's edge are vanishing from our view, their final photons reaching us as faint whispers before the curtain falls. In a sense, we're living in a fleeting golden age of cosmology, perched in the narrow window when the universe is both old enough to support life and young enough to still bear traces of its birth. Future civilizations won't just lack neighbors, they'll lack context, stranded in a present severed from the past by the accelerating expansion of space itself. Yet there's a strange beauty in this solitude. A civilization facing such a sky would craft myths unlike any we've known. Stories where the cosmos begins and ends with their galaxy, where the void isn't emptiness but the natural state of existence. Their science might invent entirely new physics to explain why the universe seems so barren, unaware that the answer lies in the unstoppable stretching of space-time. And perhaps in some distant epoch when the last stars fade, the universe's final observers will gaze into the darkness and wonder, were we always alone, or did the cosmos forget its own history? The tragedy isn't just their isolation, it's that the universe, in its relentless expansion, will have erased its own story, leaving civilizations of the far future to puzzle over a sky with no answers. We're among the privileged few who still glimpse the larger tapestry, catching the last echoes of a cosmos that won't stay visible forever. So when you look up tonight, remember, those glittering dots aren't just stars. They're vanishing ink on a cosmic manuscript, fading as you read. Dark energy might be the universe's quietest force, right now gentle enough to let galaxies cling together, subtle enough to go unnoticed for billions of years. But what if it's not just steady? What if it's growing stronger, silently amassing power until it can shred reality itself? This nightmare scenario is called phantom energy, a hypothetical form of dark energy so aggressive it could unravel the cosmos in a cosmic blink, just 22 billion years from now. That might sound like an eternity, but on the universe's timeline, it's barely a footnote. The sun will still be shining when the countdown to oblivion begins. Here's how phantom energy turns expansion into apocalypse. Ordinary dark energy, as mysterious as it is, has a constant density. Its push stays uniform as space grows. But phantom energy is different. Its density increases over time, like a spring coiling tighter the more you stretch it. The result, expansion doesn't just accelerate, it explodes exponentially, each moment adding more fuel to the fire. Picture a snowball rolling downhill, except the hill gets steeper with every turn, and the snowball grows heavier instead of melting. Soon, nothing can stop it. The math is terrifyingly simple. If phantom energy's equation of state, a number describing its pressure to density ratio, dips just slightly below -1, its repulsive gravity becomes self-reinforcing. Space doesn't just expand, it overpowers every other force in existence. First, galaxy clusters lose their grip on each other, flung apart like debris in a hurricane. Then, individual galaxies unravel, their stars ripped from spiral arms and hurled into the void. Next comes the dismantling of solar systems, planets torn from their orbits, moons wrenched away from their parents. But the horror doesn't stop there. As phantom energy's grip tightens, even atoms can't hold together. Electrons are ripped from nuclei, protons shredded into quarks, space-time itself stretched so violently that the very concept of particles loses meaning. In the final moments, the universe wouldn't just fade into cold darkness, it would shatter, a cosmic pane of glass fractured into infinite, disconnected shards. The Big Rip isn't an ending, it's an unmaking where even the fabric of reality is no longer safe. What's chilling is how plausible this scenario is. Current observations can't yet rule out phantom energy. The universe's acceleration could be hinting at something far worse than we've imagined. And if it's real, the countdown isn't just theoretical, it's already ticking. 22 billion years might seem distant, but in cosmic terms, it's a sprint. For context, complex life on Earth took barely 500 million years to evolve. The universe, in its old age, could annihilate itself in less time than it took to go from single-celled organisms to civilizations. Yet here's the twist: phantom energy isn't just doom. It's a paradoxical clue. If the universe can end this way, it tells us dark energy isn't just a passive backdrop. It's dynamic, evolving, maybe even alive in some abstract sense. Each measurement of supernova, each map of galaxy clusters, is a test of whether our fate is slow dissipation or violent rupture. And until we know, the universe holds its breath, balanced on the edge between a whisper and a scream. The idea of an expanding universe is mind-bending enough, but what if ours isn't the only one? Imagine a boundless cosmic foam, bubbling endlessly with pocket universes, each expanding at its own pace, governed by its own laws. This isn't science fiction, it's a startling implication of eternal inflation, a theory suggesting that the Big Bang wasn't a one-time event but a single eruption in an endless cycle of creation. In this picture, our universe is just one bubble in a frothing multiverse, its expansion rate set by the random conditions of its birth. Some bubbles might inflate wildly, their space stretching so fast that stars never form. Others could collapse almost instantly, snuffed out before time begins. Ours, with its Goldilocks expansion, not too fast, not too slow, or just happened to hit the sweet spot for galaxies, planets, and life. But here's the kicker: eternal inflation doesn't just predict other universes, it demands them. The mechanism that sparked our cosmic expansion, driven by a repulsive energy field called the inflaton, never truly shuts off. Instead, it keeps spawning new bubbles like a chain reaction, each one pinching off into its own separate spacetime. Picture a pot of water boiling over, with steam bubbles forming, expanding and floating away, except the pot is infinite and the boiling never stops. In some of those bubbles, the inflaton's energy decays gently, allowing for the slow, structured expansion we see. In others, it lingers too long, stretching space into a barren void or snapping it shut like a cosmic mousetrap. This means our universe's expansion rate might not be special, just one roll of the dice in a game with infinite players. The multiverse could contain realms where dark energy is weaker, leaving galaxies huddled close or stronger, ripping atoms apart before life can blink into existence. Some might even harbor entirely different physics, where space contracts instead of expands or where time runs backward. The unsettling beauty of this idea: we'll never see those other universes. The space between bubbles expands faster than light can cross it, wrapping each cosmos in an impenetrable veil. Our universe's expansion, then, isn't just a feature, it's a fence, locking us into our own pocket of reality. Yet there's a tantalizing clue that this wild theory might be right. If two bubble universes ever collided in the early chaos of inflation, the impact could have left a bruise on the cosmic microwave background, a strange, circular pattern in the afterglow. Astronomers have scoured the CMB for such anomalies, and while none have been confirmed, the search itself reveals how seriously science takes the multiverse. After all, if eternal inflation is real, then everything we know, every galaxy, every law of physics, is just a local ordinance in a far vaster, stranger metropolis of realities. So when we measure the Hubble constant or track dark energy's push, we might not just be studying our universe's fate. We could be reading the signature of a cosmic lottery, one where trillions of other universes drew different numbers. And somewhere out there, in the infinite foam of creation, another version of reality might be expanding faster, slower, or not at all, each one a silent testament to the unthinkable diversity of existence. The universe's grand finale won't be a dramatic explosion or a sudden collapse, it'll be a slow, silent fade, where even the mightiest structures surrender to the relentless march of time. Picture a cosmos so old that stars are extinct, galaxies have disintegrated, and the last flickers of starlight vanished eons ago. All that remains are supermassive black holes, the final survivors in a sea of darkness, orbiting each other in the void like ghostly sentinels. These cosmic titans, once the engines of quasars and the anchors of galaxies, will be the last organized structures in existence, lonely monarchs of an era stretching 100 quintillion years into the future. Here's how their reign unfolds. As expansion accelerates, even the tightest galactic cores unravel. Black holes that once feasted on stars and gas now wander an increasingly empty universe, their growth stunted by the scarcity of matter. With nothing left to consume, they begin their slow decay, leaking energy through Hawking radiation, a quantum quirk that causes black holes to evaporate particle by particle. The smaller ones vanish first, popping out of existence in bursts of gamma rays, but the supermassive ones, weighing billions of suns, linger far longer, their evaporation timescales so vast they make the current age of the universe seem like a blink. Now imagine the view from one of these black holes in the far future. The sky is pitch black, not a single star left to twinkle. The cosmic microwave background, once a faint whisper of the Big Bang, has redshifted into nothingness, its wavelength stretched longer than the observable universe itself. Even the protons that make up matter, if any still exist, will have decayed into subatomic ash. Only the black holes endure, their event horizons glowing faintly with the heat of their slow dissolution. It's a universe stripped to its barest bones, where time itself loses meaning, measured only by the ticking countdown of each black hole's evaporation. The math behind this decay is both beautiful and haunting. A black hole with the mass of our Sun would take 10 to the 67 years to evaporate. But a supermassive one like Sagittarius, a star at the Milky Way's heart, that could take 10 to the 100 years, a number so large it dwarfs every other timescale in cosmology. To put that in perspective, if you wrote out 10 to the 100 in zeros, it would fill volumes thicker than all the books in human history combined. And throughout that unimaginable span, these black holes will be the universe's only landmarks, their gravity the last echo of structure in an otherwise featureless void. Yet even they won't last forever. As a black hole nears the end of its life, its evaporation accelerates, its event horizon shrinking until, in a final flash of radiation, it winks out of existence. With it dies the last trace of the galaxy it once ruled, the last memory of stars and planets and life. The universe becomes a near-perfect vacuum, its energy density vanishingly low, its temperature approaching absolute zero. What remains, perhaps a sparse sea of photons and neutrinos, stretched so thin by expansion that each particle might as well be alone in the cosmos. This is the black hole era, not the end of the universe, but the last chapter where anything recognizable still exists. Beyond it lies the dark era, a timeless expanse where even quantum fluctuations might cease and entropy reaches its maximum. But for now, in this far future vignette, the black holes stand as tombstones to a vanished cosmos, their slow evaporation the universe's final act of storytelling before the curtain falls on everything we've ever known. Physicists have a name for the most glaring mismatch in science, a problem so severe it makes even seasoned researchers wince. It's called the cosmological constant problem, and at its core lies a number so catastrophically wrong that it defies all reason. The vacuum energy predicted by quantum theory exceeds what we observe in reality by a factor of 10 to the 120. That's a 1 followed by 120 zeros, a discrepancy larger than any other in physics. If our best theories were a dart throw, this would be like aiming at a board the size of the solar system and missing by the distance to another galaxy. So what's causing this cosmic embarrassment? Let's break it down. Quantum mechanics tells us that empty space isn't truly empty, it's a frothing sea of virtual particles popping in and out of existence, each contributing a tiny bit of energy to the vacuum. When you add up all these fluctuations, you'd expect space itself to curve violently under the weight of this energy, warping the universe beyond recognition. But observations show the opposite. The vacuum energy we actually measure, Einstein's cosmological constant, is almost zero, allowing galaxies to form and life to exist. The mismatch isn't just a minor tweak, it's as if you calculated the weight of a feather and got the mass of a black hole instead. Here's where things get even more bizarre. The cosmological constant isn't merely small, it's suspiciously small, fine-tuned to a precision of 1 part in 10 to the 120. If it were even slightly larger, galaxies would have been ripped apart before they could form. Slightly smaller, and the universe would have collapsed long ago. This razor-thin margin hints at something profound. Either our understanding of quantum fields is catastrophically incomplete, or some undiscovered mechanism is quietly cancelling out nearly all of vacuum energy's effects, leaving behind only the faintest whisper we now detect as dark energy. Theorists have thrown countless ideas at this puzzle. Some propose an as-yet undetected symmetry in nature that precisely zeroes out vacuum energy, a cosmic accountant balancing the books down to the last decimal. Others suggest the universe isn't just one but many, part of a multiverse where most regions self-destruct from excessive curvature, and only freakishly rare patches like ours survive by sheer statistical luck. Then there's the radical notion that gravity behaves differently on quantum scales, muting vacuum energy's impact, but so far none of these solutions have stuck, leaving the problem wide open. What makes this especially humbling is how fundamental the gap is. The cosmological constant sits at the crossroads of our two most successful theories, quantum mechanics and general relativity, yet their combined predictions are off by a factor unimaginable in any other field of science. It's like building a bridge where the blueprints say it should weigh 1,000,000 tons, but when you step on it, the boards barely creak. Either we're missing something essential about how the universe stitches together space and energy, or reality is playing a trick on us, hiding its true nature behind a veil of unimaginable precision. For now, the cosmological constant problem remains physics' ultimate reality check, a reminder that for all our progress, the universe still holds puzzles so deep they border on the absurd. And until we crack it, every calculation involving vacuum energy comes with an asterisk the size of the cosmos itself. At first glance, the universe seemed to be caught in a paradox so baffling it threatened to upend cosmology. Some stars appeared older than the universe itself. The math was brutally simple: measurements of globular clusters, ancient groupings of stars in our galaxy, suggested ages around 16 billion years, while early estimates of cosmic expansion pegged the universe at a mere 10 to 12 billion. How could stars exist before the cosmos that birthed them? This was the age crisis, a glaring inconsistency that kept astrophysicists awake at night in the 1990s, questioning whether our entire cosmic timeline was wrong. The resolution came down to a single number, the Hubble constant. This critical value, which describes how fast the universe expands, was notoriously slippery to pin down. Earlier measurements relied on galaxies close enough to track their motion directly, but these local readings clashed with inferences from the cosmic microwave background, the afterglow of the Big Bang. The discrepancy wasn't just a minor error, it implied radically different expansion histories. A higher Hubble constant meant a younger, faster-stretching universe, while a lower value suggested a more leisurely, older cosmos. For years, these two approaches refused to reconcile, leaving stars and the universe trapped in an impossible age gap. Then came the breakthroughs, improved telescopes like Hubble, fittingly named for the man who first uncovered cosmic expansion, delivered sharper observations of distant supernova and Cepheid variable stars, celestial yardsticks that helped recalibrate distances across the cosmos. Meanwhile, satellites like WMAP and Planck mapped the cosmic microwave background with unprecedented precision, revealing subtle patterns in the infant universe's glow. Together, these data streams converged on a Goldilocks value for the Hubble constant, around 70 kilometers per second per megaparsec. This sweet spot stretched the universe's age to 13.8 billion years, just enough to give those ancient stars breathing room. But the real hero of this story wasn't just better instruments. It was the recognition that cosmic expansion isn't uniform. Dark energy's accelerating push means the universe spent its youth expanding slower than we'd assumed, effectively buying extra time for stars to form. Imagine a runner who starts a marathon at a leisurely pace, then suddenly sprints the final miles. Their average speed might not reflect how long they actually took. Similarly, the universe's early, slow stretch allowed globular clusters to assemble before expansion hit the gas pedal, resolving the age crisis without rewriting stellar physics. The implications ripple far beyond fixing a math error. This recalibration revealed how delicately our cosmic history hangs on the precise interplay of expansion and gravity. A slightly faster early expansion would have left stars unborn. A slower one might have collapsed the universe before life could stir. That 13.8 billion years isn't just a number. It's the narrow ledge between a barren cosmos and one rich enough to question its own origins. And hidden in that adjusted timeline is a humbling truth. Even the universe's age is a story written in the fine print of light, waiting for us to read it right. Close your eyes for a moment and listen, not to the sounds around you, but to an echo from the dawn of time itself. Scientists have taken the faintest whispers of the early universe, the primordial density waves imprinted on the cosmic microwave background, and scaled them up 50 octaves until they become audible to human ears. What you're hearing isn't just noise, it's the literal vibration of space-time, the bassline of creation, a sonic fossil from when the cosmos was a seething plasma just 380,000 years old. These oscillations, once silent pressure waves propagating through the infant universe, have been stretched by expansion into the vast cosmic web we see today, a celestial symphony written in the language of gravity. Imagine the early universe as a colossal musical instrument, with regions of slightly denser gas acting like drumheads vibrating under the competing forces of gravity and radiation pressure. Each compression and rarefaction sent waves rippling outward at nearly half the speed of light, their peaks and troughs encoding the seeds of future galaxies. Now, 13.8 billion years later, those same waves have been frozen in place by cosmic expansion, their wavelengths stretched from the size of star clusters to the gaps between superclusters. The sound of creation didn't fade. It got locked into the very architecture of reality, translated from vibration to structure on the grandest possible scale. Here's how the transformation happened. As the universe cooled and atoms formed, photons finally broke free from the plasma, leaving behind an imprint of those density waves as subtle temperature variations in the cosmic microwave background. Regions that were once compressed, the crests of these primordial sound waves, became the gravitational wells where matter would later collect, while the troughs expanded into the voids between galaxies. The characteristic scale of these fluctuations, about 500 million light-years, acts like a cosmic tuning fork, a standard ruler etched into the distribution of galaxies across the sky. What's astonishing is how perfectly this matches observations. When astronomers map millions of galaxies in projects like the Sloan Digital Sky Survey, they don't see random scatter. They find galaxies clustered at intervals that mirror the original wavelength of those sound waves. It's as if the universe took its first chords and stretched them into a labyrinth of walls and filaments, with galaxies perched like musical notes on the staff of spacetime. Even more remarkably, the exact properties of these waves, their amplitude, their harmonics, reveal the composition of the early universe with precision, confirming the mix of ordinary matter, and dark energy we've inferred from other observations. But why scale these waves into audible sound? Beyond the sheer awe of hearing creation's soundtrack, sonification makes cosmic patterns visceral. Our ears detect harmonies and rhythms that our eyes might miss in visual data plots. That deep bass rumble you hear in the scaled-up recordings, that's the fundamental frequency of the young cosmos, the resonant pitch of a universe dense enough to carry sound waves. The higher overtones, the clinks and chimes, reflect smaller-scale ripples that would eventually become galaxy clusters and superclusters. Together, they form a chord as fundamental as the universe itself, a major triad written not in notes but in the births and deaths of stars. This sonic time capsule also resolves a cosmic mystery. Before these measurements, some theorists worried that the distribution of galaxies might be too smooth to match Big Bang predictions. But the acoustic peaks in the CMB provided the missing link, proof that tiny density variations really did grow into today's large-scale structures. The sound wave's signature even reveals how fast they were traveling, which in turn tells us how hot and dense the early universe was. It's forensic astronomy at its finest, reconstructing a crime scene where the victim is space-time itself, and the evidence is written in vibrations that have taken billions of years to decode. So when you listen to these eerie tones, remember, you're not just hearing history, you're experiencing the blueprint of existence, the moment when randomness crystallized into order, when the formless became form. Every galaxy, every filament in the cosmic web is a frozen note in this symphony, a composition begun in fire and stretched into silence by the relentless expansion of the universe. And somewhere out there, new vibrations are forming, new structures taking shape in a song without end. The universe doesn't end with a bang or even a whimper, it ends with a sigh. A slow, quiet exhale of energy so stretched and diluted that even time loses meaning. This is heat death, the ultimate fate of our cosmos if dark energy keeps accelerating expansion unchecked. Picture a bath left to cool overnight. The warmth doesn't vanish, but it spreads so thin that the water eventually matches the temperature of the room, leaving no usable heat to draw from. Now scale that up to cosmic proportions. Over trillions of years, galaxies will drift beyond each other's horizons. Stars will burn out, and black holes will evaporate, leaving behind a vast, near-empty void where particles are so far apart they might as well be alone. The universe won't be cold because it lost energy, it'll be cold because all that energy is irretrievably scattered, like a single drop of ink in an ocean. But what if heat death isn't the only possible ending? Some theories suggest the cosmos might recycle itself, like a phoenix reborn from its own ashes. In cyclical models, the universe could collapse back in a big crunch, reigniting another Big Bang, or bounce directly from contraction to expansion without singularity. Imagine a pendulum swinging between creation and destruction, each cycle leaving subtle echoes in the fabric of space-time. The appeal is poetic. Rather than fading into eternal stillness, the cosmos pulses with periodic rebirth, its laws and constants resetting with each iteration. Some versions even propose that dark energy could reverse course, its repulsive push flipping into an attractive pull, dragging everything back together in a cosmic reset. The evidence for these competing destinies lies in the fine print of expansion. Heat death hinges on dark energy's behavior remaining constant or strengthening, while cyclical models require mechanisms like quantum gravity effects near infinite density that are still speculative. Yet tantalizing clues linger. If the universe had a previous cycle, its gravitational waves might have imprinted faint swirls in the cosmic microwave background, a ghostly fingerprint waiting to be found. Alternatively, subtle variations in the distribution of galaxies could hint at a cosmic bounce in our past. For now, these ideas lie at the edge of theory, but they reframe heat death not as an inevitability, but as one possibility in a multiverse of endings. What's haunting is how these scenarios redefine permanence. In heat death, every structure, every memory of the universe's history dissolves into equilibrium. But in a cyclical cosmos, even if life, stars, and galaxies are erased, the potential for rebirth lingers. It's the difference between a story with a final period and one written on an endless scroll. And buried in that distinction is a profound question. Does the universe favor entropy, or does it hide a deeper rhythm, a pulse we've yet to detect? The answer might lie in the silent expansion of space itself, stretching our future thin, or curling it back into a seed for beginnings anew. From galaxies fleeing faster than light to phantom energy that could shred reality itself, the universe's expansion isn't just a scientific concept, it's a grand, unfolding drama that rewrites our understanding of existence. Think about this. Every second, space itself grows larger, carrying distant worlds beyond our cosmic horizon forever. Dark energy, that enigmatic force driving this acceleration, makes up nearly 70% of the universe's contents, yet we still don't know what it is. And the most humbling truth, we're trapped in a mere 3% sliver of the observable cosmos. with 97% already lost to the void, their light stretched into oblivion by the relentless stretching of space-time. What's truly astonishing isn't just the scale of these revelations, it's how recently we've uncovered them. A century ago, we didn't even know other galaxies existed. Now we've mapped the afterglow of the Big Bang, heard the echoes of primordial sound waves, and deduced that the universe has no center, no edge, and no pause button. These aren't just facts, they're testament to human curiosity's power to peel back layers of reality, to stare into the abyss and decode its secrets. Consider the Hubble tension, a discrepancy in cosmic expansion rates that might hint at entirely new physics. Or the Great Repeller, a void so vast its absence pushes galaxies like our own across the cosmos. These discoveries didn't come from passive observation, they demanded bold questions, relentless skepticism, and instruments precise enough to measure the universe's whisper. Yet for all our progress, the cosmos remains gloriously mysterious. Why does dark energy dominate now after billions of years of gravity's reign? Could phantom energy one day tear atoms apart? Is our universe just one bubble in an infinite multiverse? Every answer spawns new questions, and that's the beauty of it. The universe doesn't exist to make sense to us. It's our job to catch up, to adapt our tiny human minds to its boundless complexity. So as you look up at the stars tonight, remember, you're not just seeing pinpricks of light. You're witnessing the aftermath of quantum fluctuations stretched across billions of years, the slow motion unraveling of space-time, and the silent tug of war between dark energy and gravity. And somewhere out there, beyond the reach of our telescopes, new mysteries wait, clues that might one day rewrite everything we think we know. Which of these cosmic truths left you breathless? Was it the galaxies vanishing over the horizon, the universe's eerie flatness, or the haunting possibility of a big rip? Drop your thoughts below, because the greatest lesson the cosmos teaches isn't just how much we've learned, but how much wonder still lies ahead.